We have Tim Roughgarden from Stanford University. We'll talk about distribution-free models of social and information networks.
Okay, thanks, Shipra. So this is joint work with a bunch of people, one of whom is in the audience, Seshadri, or Sesh, and then also with some my colleague in math at Stanford, Jacob Fox, and several PhD students, Rishi Gupta, Fan Wei, and Nicole Wine. Okay, so distribution-free models of social and information networks. So what do I mean by social and information networks? I just mean networks where the edges represent relationships between people or the flow of information. And so you're all familiar with lots of examples, right? Facebook, if you want, you can think of it as a graph, with the vertices being the people and the edges being the relationships. You can think about Twitter and the graph of who follows whom, and so on and so forth. So it's really not much of an exaggeration to say, in the 21st century computer science, social network analysis has been one of the sort of major new themes that's come up over the past 10 to 15 years. Sort of systems to have these big social networks, data collecting them, and then studying their properties. And so there's a huge community that thinks about social networks, and one thing pretty much everybody can agree on, maybe the only thing that pretty much everyone can agree on, is that social networks are in some sense special. They have special structure, meaning they're not worst-case graphs. They're not arbitrary. They have predictable features that you see over and over again in different application domains. So it seems to require some kind of special model to capture the structure of social networks. But the 20th century random graph models aren't good enough. So if you look at like Erdos-Renyi random graphs, they really don't resemble the accepted qualitative features of social networks. You really need a different model. So there's also a pretty good consensus about what these high-level predictable features are of social and information networks. So I've given you sort of a list here. So the one you've maybe heard the most about is a heavy-tailed degree distribution, for example, like a power law. Another thing you hear a lot about, of what makes social networks special is community structure. So the idea that they'll have dense subgraphs indicating a community, much more richly connected internally than externally. Triadic closure I'll have a lot more to say about. That's the property that two hot paths tend to close into triangles, or if you like, friends of friends tend to be friends themselves. And then finally, there's the small world property. You can get from anywhere to anywhere else with a surprisingly few number of hops. Okay? So this is sort of the most studied and most agreed upon qualitative features of why social networks are special. But once you actually try to drill down and posit a specific mathematical model to articulate this structure, all of a sudden the consensus goes away. And there's literally dozens of different competing camps. So different generative or probabilistic models meant to suggest what social networks generally look like. So just to give you a sense, so 10 years ago there's a nice survey written by Chakrabarty and Faloutsos, and back then, 10 years ago, they singled out 23 different generative models to talk about in their survey and compare along different axes. And we see multiple new models proposed almost every month. So 10 years later, there's many more than 23. And if you think about it, this sort of poses a challenge to doing theory, which is relevant to social and information networks, because it's really not clear which, if any, of these models one should believe. And it's not like things are going toward consensus, right? The physicists sort of have their favorite models, computer scientists have their favorite models, so it seems like we're going to be stuck with this proliferation of generative models for a while. And so when we started this research project, we did want to prove results about social and information networks, algorithmic results, structural results. What we certainly did not want to do was assume one of these specific probabilistic models. We didn't want to run the risk of proving results that were an artifact of the specific distributional assumptions. We wanted to sort of capture something more fundamental that's going on no matter which generative model you believe in. So that naturally led us to the following research program. We said, well, what's sort of the intersection of the properties of all of the generative models that people ever think about? So what properties does every single motivating generative model possess? Secondly, do those minimal properties alone in the intersection already enable any non-trivial results, structural results or algorithmic results? And so really what we were trying to do is have a framework that would let us prove theorems that would be sort of relevant simultaneously across any generative model you might care about, both the ones of today and the ones that will inevitably be proposed tomorrow. Okay? So that's sort of the high-level research program I'm going to tell you about. Let me digress for one slide just to explain how this sort of connects to the themes of this week and more generally this special semester. So one of the major themes of this semester is beyond worst case analysis. The idea of proposing alternatives to worst case analysis to get better advice about which algorithm is better than another one. And one of the things which has worked really well in that field is something I like to call hybrid models. So for example, the whole second half of my bootcamp tutorial was about hybrid models. And this is a way to combine both worst case and average case aspects. And so what you do with hybrid models is you seek out an algorithm which is simultaneously good for a wide range of distributions. Okay, so you have in your mind some class of distributions over inputs. An adversary, if you like, picks which distribution from that class input's actually being generated from. You don't know which one. You have to come up with an algorithm which is almost as good as the best for that distribution, no matter what the distribution is. And there's lots of examples of these hybrid models. Famous ones you've probably heard about, like smooth analysis, semi-random models, prior independent auctions, and so on. And really, this was kind of, you could imagine coming up with our research program without thinking this way, but this was really the lens through which we were looking when we formulated these goals. We really sort of, in effect, wanted to take a worst case over all plausible generative models of social networks and have a single algorithm or a single structural result, which was true simultaneously for all of those distributions. Now, in the work I'll describe, there aren't actually any distributions. We focus on sort of deterministic conditions that are going to hold with high probability in all these, over all the generative models. But this was still kind of how we arrived at this line of work. OK, so we're going to focus on triadic closures. Let me return to that. That was the third of the 4 properties I listed at the beginning about what's special about social networks. So again, triadic closure means in social networks, 2 hot paths tend to close into triangles, or if you like, friends of friends tend to be friends. So this is an old idea. It was popularized in a very influential paper by the sociologist Mark Granovetter back in 1973. It was discussed before then as well. And it's easy to sort of tell anecdotes about why in a social network you probably would expect actually triadic closure. All right, so suppose I tell you that 2 people are friends. What else is probably true? Well, it probably means they interact with each other through their mutual friend, and it's much more frequently or likely that they'll interact than 2 random people in the network. Moreover, the fact that they have a common friend makes it likely they'll be similar in some sense, like have shared interests, which makes it more likely they'd want to be friends with each other. Or maybe even they feel pressure to be friends because they don't want to exert any stress on the friendships they already have with the common friend. So there's lots of stories about why you might expect this, but those are just stories. But if you go to the data, you really do see plenty of evidence for this triadic closure property. So this is one plot of one standard social network, but you get similar plots for lots of other social networks in lots of different domains. So this is the network of email communications at Enron some years ago. And here's what the plot shows, okay? So what I've done is I've bucketed pairs of vertices of this network according to how many common neighbors they have. Okay, so there's some vertices that have no neighbors in common, and then there's some pairs of vertices that have lots of neighbors in common. So that's the x-axis. The y-axis is in a given bucket for a given number of common neighbors, what fraction of those pairs are themselves connected. Okay, so that's what I'm calling the closure weight. So the fraction of pairs with a given number of common neighbors that are themselves connected. And what you see is this very clear trend that as 2 nodes have more and more common neighbors, they're more and more likely to be directly connected. Okay? Now, so what would this plot look like on a Erdős-Rényi random graph with edge density p? Would it look like this? No. Yeah. Flat. It would be flat. Okay, it would be flat with a line at the edge density p. Why? Edges are independent. Right, so condition on the number of common neighbors of 2 nodes, it tells you nothing. The probability they're connected is exactly p. Okay, so this is one of the senses in which Erdős-Rényi is really not a good model for the types of properties you see in actual social networks. Okay, so somehow we want to be thinking about graphs whose plots look something like this. So I'm going to give you 2 different definitions, 2 different graph models, kind of motivated by this type of triadic closure property. Before I get into those details, let me just spend one slide sort of saying why did we focus on triadic closure. One reason is just as social networks go, it's one of the more uncontroversial things you could pick to assume. There's a consensus, it's basically one of the most universal signatures of social networks. But you're probably wondering, why didn't we talk about power law graphs, which is maybe the property you hear the most about. And the first reason is just for the types of problems we were motivated by, and we were really thinking about sort of community detection-like problems, which is what people tend to obsess over in social network analysis, so things like dense subgraph or clique. Assuming a power law distribution doesn't really help. Okay, so hard problems remain pretty hard if all I know about a graph is that it has a power law distribution, okay, and it's otherwise worst case. So as we'll see in one of our graph classes, you can actually find the maximum clique in polynomial time. And that's certainly not true. None of our results are true, just assuming only a power law distribution. So that said, so our initial work was done in 2014, but just this year, there's subsequent work which is showing that at least for other problems, specifically for problems inside P, this actually is an interesting assumption. So you make an assumption that a graph has a power law degree distribution, no other assumptions, and it turns out with just that assumption, there's lots of graph problems which you can speed up over the best algorithm, the best running time known for the worst case. Okay, so lots of problems where you need, say, n squared on worst case graphs, but you can get much closer to linear, assuming only a power law degree distribution. And this is true for lots of problems. Transitive closure, matching, metric problems like diameter and radius, and so on. So that's been a just interesting recent, very recent development on the power law degree side. But again, for us, for the problems we cared about, triadic closure was the one that had bite, was the one that actually gave you a foothold to prove interesting results. Okay, so the rest of the talk, I'm going to give you two different, sort of graph classes that are meant to capture triadic closure in different ways. And for each one, I'm going to highlight one result that we've proved. So one structural result in the first part and one algorithmic result in the second part. So anyone want to ask any questions before I get a little more precise, a little more mathematical?
So triadic closure itself doesn't really define it?
Yes, yeah. Yeah, so far I've just given you the intuition that, if you know that two pairs have a common neighbor, they're more likely, in some sense, to be connected than if they don't.
The graph that you showed before, it's surprising that it's completely linear.
Right. It is, yeah. So I picked, a lot of the plots look roughly like that, but it is sort of remarkable. But we're not going to assume a linear dependence, as you'll see.
It cannot be linear forever, of course, because it reaches.
Yeah, well, at some point there's no more pairs of nodes with that many common neighbors. So, yeah.
So is there some sense of the strength of this connection? Because on Facebook, a lot of people tend to connect to each other because Facebook suggests stuff, but it's like some very
good question. Yeah. So and this is especially relevant because I brought up the Granovetter paper, and he was really concerned. So the paper is called the strength of weak ties. So he made this distinction between strong and weak ties, which we will not be making. I think that'd be a very interesting direction to take this work. So we're just looking at the binary. Are they connected or are they not? But you could imagine weights and so on. So okay, good. So, triangle-dense graph. So the formal definition's simple enough, but let me just show you a cartoon. Let me relate it back to the plot we just saw of the closure rate as a function of the number of neighbors in the Enron graph. So in effect, we want a definition which sort of says, let's only worry about graphs whose plot looks something like this. But as I was telling Yossi, we don't want to make an overly restrictive assumption. That would sort of defeat the point. So we're not going to assume a linear relationship between the x and the y-axis. That would be way too strong. So we're going to sort of look at two different coarsenings of what these plots look like. And for the first one, in effect, what we're going to do is rather than bucket pairs of vertices by their number of common neighbors, we're just going to distinguish between pairs of vertices with no common neighbors and those that have one or more common neighbors. And the assumption is going to be, on average, over pairs of neighbors that have over pairs of vertices that have at least one common neighbor, you should see a decent closure rate. Okay, some parameter t bounded away from 0. Okay, so imagine we're sort of averaging this plot all over here, and then what's forbidden, right? So basically we want graphs whose plot lies in this green shaded region. So what's forbidden is that pairs of nodes with at least one common neighbor have a very small closure rate. Okay, that's the one thing we're forbidding in this graph class. So let me really make it precise though. Okay, so we make it precise through the transitivity of a graph. So this is an old notion, also called the global clustering coefficient. And so this is a number between 0 and 1. And it's just the fraction of the two hop paths in the graph that actually are in triangles, okay, that are filled in. All right? So formally, you look at 3 times the number of triangles over the number of not necessarily induced two hop paths. The 3 is because each triangle contributes 3 different two hop paths. Okay? So, for example, if you have cliques or unions of cliques, every two hop path is filled in. Right? So that would be transitivity 1. And it's easy to see the converse. Okay, the only way to have transitivity 1 is to be the disjoint union of cliques. The path, nothing's filled in. So that would be transitivity 0. And more generally, any bipartite graph would have transitivity 0. Okay? So the graph class we're going to be talking about, which is going to be parameterized by this transitivity, but loosely speaking, we think of an infinite family of graphs, we call it triangle-dense, if the transitivity of the graphs is bounded away from 0, even as the graph size grows large. Okay? So you have to choose, what is the threshold. You have to choose what transitivity you're setting as the lower bound. So there's one parameter in this definition. Okay? But say, 0.1 or something like that. You insist that the transitivity stays bounded above 0.1 even as the graphs grow arbitrarily large. Okay? So that's going to be the first graph class, triangle-dense graphs. Okay. All right, so a few questions. Whenever you put down a definition, you've got a lot of work to do justifying your existence. Why this definition, not some other one? So first of all, okay, so do real social networks actually satisfy this property? Are they triangle-dense? So, in an impressive feat of engineering, Ugander et al. Actually computed the transitivity of the Facebook graph, and they found it was 0.16. You see that, you might be wondering, okay, is that a big number or a small number? How should I interpret that? And so to help interpret it, let's remember we're talking about quite sparse graphs. So this is a graph whose edge density is less than like 10 to the minus 5. So a random graph with this edge density would have transitivity only 10 to the minus 5 or less. We're seeing more than 4 orders of magnitude higher transitivity in the Facebook graph. So that's pretty strong triangle density. Okay? And you can do the same exercise with other social networks and you get the same kind of thing. Okay? So at least for constants bounded away from 0, it does seem like real social networks satisfy this definition. So that's great. So what can we say about them? So for this, I just, the main result of this first talk is going to be structural. And the main point of the structural theorem is to help us kind of understand or visualize what these triangle-dense graphs look like in some sense. And so the kind of inspirations I have in mind here are like separator theorems for planar graphs. They kind of say you can more or less think about a planar graph as a grid, generalized grid. Or like the regularity lemma, which is a way of saying you can think about dense graphs as basically being like random graphs. So how should we think about these triangle-dense graphs? Well, so one sort of starting point would be to remember what we said, that the transitivity is equal to 1 if and only if the graph is a disjoint union of cliques. So you might hope for like a robust version of that statement, saying that the transitivity is high if and only if it roughly looks like an approximate union of cliques. Okay? So maybe they're not totally disjoint, maybe they're not totally cliques, but this is sort of what we have in mind as a hopefully a canonical triangle-dense graph. But then you start playing around with the definition, and you realize it's actually a very weak condition. So you realize there's actually some pretty weird graphs which have high triangle density. Okay, so we're really not assuming that much. One simple one would be take a clique on, say, root n vertices, and then attach a really long path to it, say with like n vertices. Okay? So the triangle density of this graph is very close to 1, because almost all of the 2-hop paths are in the clique, but almost all of the nodes are in this long path which doesn't resemble social networks at all. Okay? So triangle density, even very close to 1, can allow for pretty weird graphs. And if you work harder, it gets weirder as well. Okay? So what's the upshot? Well, I've argued that having high transitivity, it's a necessary condition to be a plausible social network. So if something's a social network, it will have decent transitivity. But the converse doesn't seem to hold. Okay? It's not sufficient to look like a social network. You can have non-social networks that happen to have high triangle density. So, and this is both a bug and a feature, the fact that the condition's so weak. If we can prove any positive results whatsoever, they kind of are immediately meaningful. Okay, it has a worst case flavor, right? So if we prove anything positive, it'll hold for any plausible social network, okay, because any plausible social network has high transitivity. And it's also going to apply to any graph which has high transitivity for whatever reason, even if it has nothing to do with social networks. Okay? So positive results automatically robust and meaningful, but of course the worry is that the condition's so weak, just nothing interesting is true. And again, sort of a cautionary tale would be, the power law distribution doesn't actually help us prove anything interesting for the kinds of results that we were looking for. Okay? So the good news is you can prove some stuff about triangle-dense graphs, so assuming nothing more than a constant fraction of the 2-hop paths are filled in. So the result I'm going to highlight is a decomposition theorem, which again will it'll make precise the idea that triangle-dense graphs are more or less like the approximate union of approximate cliques. Now from that lollipop graph, we know we need to be a little bit careful with how we make the statement, but some statement of this form is going to be true. Intuitively, what the theorem is going to say, it's going to say that in a graph with high transitivity, you can cover kind of most of the interesting stuff in the graph with dense, tightly knit clusters, dense, tightly knit clusters. Okay? So you can cover most of the interesting stuff with disjoint, tightly knit clusters. Let me be more precise. So give me a graph with healthy triangle density. I'm going to find a collection of disjoint-induced subgraphs. I want to emphasize these subgraphs are not a partition in general of the vertices. They only cover part of the vertices in general, but they're going to be disjoint. Each of these induced subgraphs is a tightly knit cluster in the sense that it has radius at most 2, in the sense that it has constant edge density and constant triangle density, where the constants here depend on the transitivity in the original graph G. Now this by itself is still not non-trivial because I could just take the empty collection. So to make it non-trivial, I'll insist that a constant fraction of the interesting stuff in the graph actually shows up, is preserved in one of these dense subgraphs. And we're going to identify the interesting stuff in the graph with the triangles of the graph. So a constant fraction of the triangles of the graph have to show up in one of these clusters. That's the sense in which you cover most of the interesting stuff of the graph. So for example, with that lollipop graph, right? So what's the decomposition going to look like? It's just going to be the clique. Okay, you're just going to throw out the path. Remember, you don't have to cover all the vertices. You just cover the clique. And then you're actually going to preserve 100% of the triangles in the graph. Okay? So that's the statement. So let me help you interpret this a little bit. So why is this interesting? So one reason it's interesting is what we said. It helps us think of triangle-dense graphs as roughly a union of cliques. And so there's a couple other implications, and I won't have time to really delve deep into these, but let me just say a few words. So first, on a conceptual level, remember way back at the beginning of the talk, I listed those 4 features of social networks. The third one was triadic closure. The second one was community structure. So a consequence of this theorem says that those 2 things are really not independent properties. If you have triadic closure properties in the form of a decent sized transitivity, it is inevitable you will have some community-like structures. You will have dense low radius subgraphs, namely the ones that are output by our decomposition. So you can think of it as a sort of local to global result. So you make this local assumption just on 2 hot paths, and yet implies a sort of more global property of having this collection of dense subgraphs. So you can also, I'll show you a bit about the proof, and you'll get the sense that the proof is also an efficient algorithm. And we've implemented the algorithm, and even if you implement it literally unoptimized immediately from the paper, you get pretty decent results. It runs pretty fast, and it's useful in various heuristics. So on the theory side, you can do things like recover planted clusterings in the approximation stable model of Balkan, Blum, and Gupta. And then empirically, we've used it for heuristics on various problems on social networks, like, for example, sampling and counting cliques. Okay? So these are some of the things that the theorem can be used for. But what I want to focus on in the rest of this first part of the talk is a little bit about the proof. So any questions about the statement first? Yeah.
Not about the statement, but when you say that it gives community-like structure, I would say that it only does if there is a small number of subgraphs. What if there are many, maybe the structures that you get out of the theorem are all the triangles.
Right.
Disjoint.
Yeah, in social network analysis, it's pretty common that the communities people find are small. So the regime of having a linear number of constant-sized communities is actually, one of the dominant paradigms in actual social network analysis. It's a very different regime than like planted bisection, and where you have 2 groups, that are sort of sparsely connected. And yeah, if you're talking about Democratic and Republican blogs, okay, that's one case where it makes sense to have 2 communities. But in most social network analysis, actually, the relevant case is a lot of small communities. So it doesn't, as far as we were concerned, that didn't bother us. We actually viewed it as a feature to have small communities. Yeah. Other questions? Yeah.
Is the definition tailored to community detection kind of problems, or does it extend to more?
So by extend, what would you mean?
So if there's some other, does it help speed up some other graph problems which don't relate to community detection?
It's unclear. We were thinking mostly about community detection algorithms. I mean, once you have a graph class, it becomes a playground. So you can take your favorite computational problem and see what is easier on this graph class. We haven't really done that systematically. And again, in this part, I'm going to focus on a structural result, not an algorithmic result. Okay. Other questions?
What are you formally thinking of, like, for a community like structure? Is it just clique or?
So in the second part, I'll be talking about cliques. I mean, for now, the statement of the theorem doesn't mention communities, right? So this is sort of an interpretation, and it's in quotes on purpose. So there's lots of standard ways to define communities, like through conductance. I'm not going to need any definitions of community because, again, my theorem just says. So the theorem, I'm not asserting semantics really to these clusters you get out. It seems likely that in most social networks they're going to correspond to communities, but that's not what we're proving. We're just proving that there are these dense structures that capture all the triangles of the graph, most of the triangles of the graph. Okay, so I'm going to leave communities undefined. Yep.
Assuming a property that you assume for any subgraph, this is too strong. This is like you can assume that the density
Right.
is large for every subgraph.
So we explored that. It doesn't help that much, actually. So I mean, it does rule out some of the particular rogues gallery examples that I showed you, which is why we looked at it. But as far as the strength of the theorems we can prove, it didn't actually help us. But, and it may be, it may still help, and we just haven't figured out how to use it. But as far as we could tell for our theorems, it didn't really buy us much more. It's a good question.
Do you mind flashing the theorem once?
Yeah, definitely. Okay. So let me say a little bit about the proof/algorithm, how it works. So the algorithm interleaves two different subroutines. And the first subroutine is driven by a notion called the Jaccard Similarity of an edge. And Jaccard Similarity is just measuring how much overlap there is between the neighborhoods of the two endpoints of an edge. So here's an edge, UV. There are 7 vertices that are neighbors of at least one of U or V. 2 of them are common neighbors. So that's 2 out of 7. That's the Jaccard Similarity. Okay, so it's just the fraction of the overall neighbors that are common neighbors. It's a number between 0 and 1. Okay? And so intuitively, if an edge is participating in lots of triangles, that's going to be highly correlated with having high Jaccard similarity. Not participating in triangles is going to be correlated in some sense with low Jaccard similarity. So the cleaner subroutine, what it does is it just gets rid of edges with low Jaccard similarity. Okay, less than some parameter epsilon. We take epsilon to be a constant fraction of the graph's transitivity. Okay? So while there's an edge with small Jaccard similarity, delete it, or an arbitrary one, and repeat until you're left with a graph where everything has high Jaccard similarity. Okay? So that's the cleaner. All right? All right, so for example, on the lollipop graph, what is the cleaner going to do? Well, these edges have Jaccard similarity 1, so it's not going to do anything here. These edges have Jaccard similarity 0, right? Because there's no common neighbors. So the cleaner is just going to rip off this whole path, which is actually exactly what we want it to do. All right? And in fact, the cleaner alone on some of the networks we looked at already gives pretty interesting decompositions. But for the theorem, we'll need a second subroutine as well. All right, so what do you have to prove about the cleaner? You just have to prove that you haven't made the theorem impossible. So the theorem is asserting you better be preserving a constant fraction of the triangles, so we better not have deleted all the triangles when we deleted these edges. So why didn't we? Well, the graph has constant transitivity. So that actually gives us a relationship between the number of 2-hop paths and the number of triangles. They're related by a constant factor. On the other hand, if an edge has low Jaccard similarity, it means that edge participates in many more open 2-hop paths than it does triangles. So when you delete an edge with low Jaccard similarity, maybe you delete a few triangles, but you delete way more 2-hop paths. And because 2-hop paths are triangles are in this constant factor relationship, this can't go on very long, and you'll be left with the constant fraction of the triangles.
You have to know the transitivity.
You need a lower bound on the transitivity. Yeah. Okay, so why do we do this? Well, once all edges have decent Jaccard similarity, the graph has some nice properties. Okay, so first of all, it's immediate that it's sort of locally approximately regular. So if you look at any edge and you look at its 2 endpoints, their degrees can't be that different, only by a factor of 1 minus epsilon. Just because if your degrees, if your neighborhoods have radically different sizes, then the overlap just can't be that big. You can't have high Jaccard similarity. So limit 2 is immediate, and then limit 3 is some simple algebra that I'll spare you from. But limit 3 already says at this point, we know there are dense substructures. In fact, take any vertex, look at its neighbors, look at its one-hop neighborhood. Already, its one-hop neighborhood is going to be dense in edges and triangles. So constant density, where the constant depends on the transitivity of the original graph. Okay? And now it kind of seems like hopefully we're done, right? So we've identified, where these clusters come from. You just get the Jaccard similarities high. You look at a one-hop neighborhood. You rip it out. The obvious thing to do is now just go back and forth. Rip out a one-hop neighborhood, clean again, rip out another one-hop neighborhood, and so on. And it seems like we get the decomposition. So what could go wrong? Well, the same thing we were worried about with the cleaner. What could go wrong is we destroy too many triangles. But in this case, actually, the fear is real. Okay, it can actually happen. This algorithm actually doesn't satisfy the theorem. And the bad example is a complete tripartite graph. Okay? So in a complete tripartite graph, every edge has pretty high Jaccard similarity. But imagine you just ripped out this bottom left vertex and its one-hop neighborhood. Notice its one-hop neighborhood is all of these vertices and all of these vertices. Well, you'd preserve some triangles, right? So you'd rip out this neighborhood, and any triangle which involves this lower left vertex, that would be preserved in the one-hop neighborhood you rip out. But you would be destroying every other triangle that involves any of the rest of the vertices on the northwest corner. Okay? So that's what happens. So you remove it, all the triangles are gone, and you don't preserve the interesting stuff of the graph. So this is sort of a natural attempt, but it's not quite enough. Happily, is a pretty simple fix, actually. So this scheme will still more or less work, but we have to supplement the one-hop neighborhood with some additional vertices from the two-hop neighborhood. Okay? So we pick a vertex, we add in all the neighbors of that vertex, and we add a few neighbors of neighbors. And we choose the set of neighbors to add exactly so that we get the property that we want, where the number of triangles that we preserve is at least a constant fraction of the number of triangles that we destroy. Now, what's not at all obvious is that there's always a way to do this, okay, that there exists a subset of the two-hop neighborhood so that you actually destroy or preserve roughly as many triangles as you're destroying. And I think that's the most unintuitive part of the proof. So you really have to prove that, but it is true. And moreover, it's just a simple greedy algorithm can be used to identify the vertices in the two-hop neighborhood that work. All right? So that's the final algorithm, which gives you the decomposition theorem. You clean, get the Jaccard similarities up to epsilon, pick an arbitrary vertex, go to the one-hop neighborhood, supplement it with a few vertices from the two-hop neighborhood, extract, clean again, extract again, and so on. And so that's what leads to this result.
If you, instead of doing, like if you go back to the left side,
yep.
If you, instead of doing the charging, just took the better of the one vertex or the entire set of all the vertices that you would be deleting together with it. Would that...
So you're proposing a specific way of choosing some of the two-hop neighborhood? Is that right?
I think what I'm saying is instead of deleting the two-hop neighborhood...
Part of the two-hop neighborhood, yeah.
Just take the entire two-hop neighborhood.
Okay.
And if like deleting it would have been bad, then taking all of it should be good. Does that make sense?
What's the intuition? I mean, I don't have good intuition about whether that's true or false.
If the first one would have deleted a lot of triangles,
yeah.
Then you should have a lot of triangles in what.
Sure, I guess the worry is that then at the next boundary you again have still more triangles between the two-hop and the three-hop neighborhood. Yeah. Which is why it's not obvious you can do this at all. So this is kind of the magical part of the proof, that there is a magical subset of the two-hop neighborhood that you don't have this problem, okay, that you really get parity between what you're saving and what you're destroying. Okay. So that was the decomposition theorem, and that was the first part of the talk. Any questions?
So, what is the running time of the algorithm that builds the decomposition?
Yeah, so we can do it in time proportional to the number of two-hop paths in the graph, so the number of wedges in the graph.
And the property itself doesn't give you a better bound, right?
Sorry, the property itself.
I mean, the high, what do you call it? The high triadic closure, right?
Right, I mean, you could imagine optimizing it, but as stated, it does enumerate all the wedges in a graph, and if it happens to be a clique, then that's going to be a lot of wedges. Now, in the actual, real social networks that we look at, the number of wedges is not that big. I mean, it's super linear, but subquadratic. Think n to the 1.5 or something like that. So on the motivating examples, it's actually quite fast.
Disjoint two-hop paths?
Disjoint two-hop paths.
It's proportional to the number of disjoint two-hop?
No, just two-hop paths. Yeah. So yeah, I mean, it could be n cubed.
Okay.
But in the motivating examples, it tends to be more like n to the 1.5. Yeah. And and needless to say, we didn't spend energy on optimizing the running time. So we really went for the, we actually just proved the theorem, and then we realized it's an algorithm, and it was one of those very happy cases where the algorithm in your proof actually just works pretty well. I'm sure you could do better by actually, trying to do good algorithm engineering. We haven't done that. Other questions?
So when you say a constant fraction of the triangles are preserved, this constant could be very small, like say 1%.
Sure.
So potentially we're throwing out 99% of the graph.
In theory, yeah.
Do you have a sense of, in practice?
Yeah, so in practice, the numbers we capture somewhere between 60 and 90% of the triangles, depending on which data set you look at. Trying to narrow the gap between the worst case, the theoretical guarantees, and what we see on the real data sets is an open question. You're right. So the quantitative bounds you get out of this theorem are not as good as you'd like. Okay, so the dependence of these constants is polynomial on the transitivity that you assume, but it's a pretty high degree polynomial. I mean, one of them is even quartic in the transitivity. We suspect the right number is between 2 and 3. If you make no assumptions other than triangle density, we think you really do need at least a quadratic degradation in terms of the transitivity. If you make more assumptions, it's totally possible you could prove stronger results.
So what kind of hard problems are easier to solve using this decomposition and the divide and conquer scheme?
Yeah, so as far as theorems about that, that's more the subject of the second talk. So I'll show in a different graph class we can compute maximum cliques in polynomial time. So here, a theoretical guarantee we can prove is not in a worst case model, but in the approximation stable model of Balkin, Blum, and Gupta, where they posit a ground truth clustering. And so in that case, we can sort of match their theoretical guarantees using this algorithm about recovering clusterings up to a small classification error. And then heuristically, it works well for some other problems, but we don't have theorems, like for counting the number of cliques or even max cut, this kind of thing. But for the first part, I really wanted to, I think the one I wanted to highlight was a structural result. The second part, it'll be an algorithmic result. So it's largely wide open to just, once you have a graph class, it's sort of a fun playground for anyone who does algorithms, right? So whatever your favorite problem is, you can start thinking about it in that class.
TSP seems to be candidates.
What's the intuition for that?
It's like finding a sign tree and then doing brute force.
That would be cool, yeah. We haven't thought about TSP. I mean, we haven't done, like I said, we haven't done sort of a systematic exploration of tons of computational problems in these classes. I think that's a totally worthy thing to do, but we haven't done that. We just sort of focused on our community detection related problems.
People think about like planar separator and TSP and doing divide and conquer in order to do that. And it sounds like that, at least. Like a different decomposition. It's not like coming up with a grid, it's coming up with this clique decomposition. And
Other questions? Yep.
Can you just repeat questions so people ask them more?
Yes, I'm terrible at that. Also, I'll try to remember. Yeah, so I mean, this question was sort of generally about kind of which algorithmic problems are easier to solve on triangle-dense graphs. And so I just talked about we have some theoretical results, we have some empirical results, but it's largely open. So we focused on the structural results here. Okay. So let me talk a little bit about our second graph class, which we call C-closed graphs. So going back to the motivating plot, so again, this was our Enron network, and it was showing that the closure rate increases with the number of common neighbors. So again, we want to look at some sort of coarser version of saying we want graphs where the plot looks like this. And so we're just going to have a threshold. Okay, so that's going to be the parameter C. And in this graph class, we're going to insist that whenever a pair of nodes has at least C common neighbors, they themselves have to be connected. So in other words, the closure rate is 100% from C onward. All right? So this is obviously a little bit of a caricature of what's true in real networks. I mean, this gets pretty large, but it's not 100%. But you get a really nice, crisp graph class if you actually with just a single parameter with this C-closed definition. Okay, so we're saying that we're looking at graphs whose plot lies somewhere in this green region. We don't care about the closure rate below C, but it better be 100% after. Okay. All right, so again, graph is C-closed if whenever you have a pair of vertices with C or more common neighbors, they're connected by an edge.
So is C a constant or does it grow with?
It can be whatever you want, yeah. I mean, I'll talk more about how to think about C, but C equal 2 is already interesting, as we'll see. So if you want, think about C as like a constant less than 10, but the results don't really need that. Yeah. Okay. So you can also think about C-closed graphs in terms of forbidden subgraphs. And indeed, if you go back to Granovetter's paper, he even talks about triadic closure in terms of what he calls forbidden triads. So for us, for C-closed graphs, what's the corresponding forbidden subgraphs? Well, they look like this. So what's not allowed is to have two vertices with no edge between them with a shared neighborhood of C or more vertices. Okay, we don't care about how these are internally connected, but if you have this structure, then you're not a C-closed graph. Okay, so that's another way to think about it. All right, so getting back to Kamesh's question of what kind of C should we think about? So notice, the bigger we take C, the weaker the condition we're imposing. Okay, that's sort of raising the threshold before any constraint kicks in. So the most restrictive class is 1 closed graphs. Once you go to n closed graphs, you get all graphs. Okay, it's not a restriction at all. Okay, so 1 closed graphs, they're actually not that interesting, right? So that says whenever you have at least one common neighbor, you have to be connected. So that just says every 2-hop path closes to a triangle. Same thing as transitivity 1. That's just the unions of cliques. So the first non-trivial thing to think about would be the family of 2 closed graphs. And again, like with triangle density, I mean, this is a weak enough condition that you start getting some graphs you kind of weren't maybe hoping for, but they show up anyways, sort of unannounced and unwelcome. So for example, imagine you have a high girth graph. By high, I mean like 5, okay? Well, if you have a girth at least 5, there is no pair of nodes with 2 common neighbors. Right? If there were, it would give you a 4 cycle. So the hypothesis of the condition just holds vacuously. All right, so for example, bounded degree expanders are already members of the 2 closed family. All right, so that's a little scary, right? We know lots of problems, kind of the hard cases expanders. So it says there's lots of problems where this assumption by itself won't help you. But again, we were really thinking about community detection type problems, and in particular, things like finding dense subgraphs, finding cliques. And notice actually, this shouldn't bother us if we're trying to compute cliques. Right? The clique problem is not a hard problem in a high girth graph. Right? The clique is just an edge. That's the max clique. Okay? So it still raises hope that maybe there are problems we care about that you could do something on C-closed graphs, and we can. As I mentioned, I'm going to show you we can actually solve clique in polynomial time for any fixed C. Okay? So we're actually going to do something more general. We're going to show how to enumerate all maximal cliques of a C-closed graph in polynomial time. And so really this just boils down to bounding the number of different maximal cliques in a graph. It's been known for a long time that you can just enumerate maximal cliques of any graph in time polynomial in the number of maximal cliques. So if you only have a small number of cliques, you actually can enumerate all of them in polynomial time. Now, of course, you can't solve clique in general, and in general graphs, you might have a lot of maximal cliques. And the canonical example here is the Moon-Moser graph. So this is just an n/3 bipartite graph. So I take a bunch of triples of vertices, and I connect each pair of vertices which are in different triples. Okay, so it's like a bunch of independent sets of size 3, and then everything else is connected. So if you think about it, you can get a maximal clique by just making one choice from each of the n/3 triples. So that's 3 to the n/3 different maximal cliques, each of size exactly n/3. Okay? And there's a nice theorem of Moon and Moser, a half-century old, which actually says this is the largest number of maximal cliques you can ever have as a function of the number of vertices n. Okay? Now this doesn't immediately stymie our goal of solving clique in polynomial time, because these Moon-Moser graphs, if you think about it, they're not C-closed for any reasonable C. If you take 2 different vertices in a common triple, they have n-3 common neighbors, yet they're not connected by an edge. Okay, so it's definitely not C-closed for reasonable C. On the other hand, this does sort of show us the best we can hope for. Just by considering Moon-Moser graphs on C vertices, which are trivially C-closed, it does show that the number of maximal cliques in a C-closed graph can scale exponentially in this parameter C, in your threshold C. Okay? So if there's going to be a positive result, it's going to have a fixed parameter tractable flavor. Okay, where the number of maximal cliques, while exponential in C, is polynomial in the other parameters describing the graph. Okay? And that's in fact exactly what we show. So we show that in every C-closed graph, the number of maximal cliques is at most n squared times exponential in C. That same Moon-Moser, 3 to the C over 3, except with the n replaced by C. Okay? So in particular, you can enumerate and therefore find the maximum clique for any constant C, even for C all the way up to logarithmic. Okay? So we have a quadratic dependence on the number of vertices. We know it has to be at least n to the 3/2. We're pretty curious where it is in between. We don't know yet. But at the very least, you get this fixed parameter tractable like upper bound. Okay? So I want to say a little bit about the proof, and then we'll be done. Any questions about the result?
So it's a more empirical question. Has anyone, for real social networks, has anyone looked at how C-closed they are?
Well, so the question is really, are they close to being C-closed? Yeah, so that's the next step to do, yeah. I mean, I showed you that plot, which says that the closure rate does get pretty high once C gets reasonably large. But, if you think about it, I mean, it's a nice algorithmic problem, actually. Suppose I give you a network and I let you add or delete edges, and you want to make it C-closed for some target C. How many edges what's the minimum number of edges needed to do that? That's presumably an NP-hard problem. We haven't proven that, but it's presumably NP-hard. But so we're trying to actually think about heuristics for approximating distance to the family of C-closed graphs. But that's the question. The question is not, are real graphs C-closed? No, because 100% is too strong. So, I mean, so that's one way of doing it. Also, I'm optimistic you could have robust versions of these theorems saying if you're close to C-closed, maybe you can't compute a clique, but maybe you can compute a dense subgraph, which is almost as big as the biggest clique, or something like that. So say a bicriterial result coming from a weaker assumption. Those are all, I mean, this is ongoing work, so it's stuff we haven't gotten to yet. That's a good question. Yeah.
You just said that you think it's NP-hard to add the minimum number of edges to get...
Add or delete.
Ah, okay.
Yeah.
Because adding would be...
Adding is not hard, yeah, that's right. So, which is one measure you could use. So that would be interesting, actually, just how many edges get added when you do a sort of closed completion on real social networks. So thanks for the suggestion. I might have an undergrad do that this year. So.
A question.
Yeah.
So can we say that the dependency on C is optimal because of the previous slide, basically, and the fact that we know?
Yes. So ignoring the n. Okay. So we know there's a lower bound which scales at least like this.
So forget about that.
Say it again.
So forget about the n squared factor.
Yeah. Then we know it has to scale like this.
Okay.
Yeah. The dependence on n we don't fully understand, but there definitely does have to be dependence on n also. We do know that. Yeah. All right. So I'm running out of time, but let me just maybe give you a quick kind of picture of at least parts of the proof. This is going to be kind of very high level in the interest of time, but just to give you the flavor of it. So it's an inductive argument. Okay, so this bound comes out of recurrence. The recurrence has two terms. Let me just kind of flash pictures about what each of the two terms come from. So for the purposes of induction, pick your graph G, your C-closed graph. Pick your favorite vertex V, I don't care which one. N, these are the vertices connected to V, its neighbors. X, these are the vertices not connected to V, its non-neighbors. Okay? And so what we're going to do is we're going to count maximal cliques in this graph in two steps. So first we're going to delete V and use induction to compute the number of maximal cliques in G minus V. So I'll skip that case. That's sort of the easy case. And so then the second case is we have to count the maximal cliques in G that we haven't counted in the inductive step when we project it down into G minus V. Okay? And basically what can go wrong, the reason you haven't counted all of the cliques is because if you start with a maximal clique in G and you look at its projection after deleting V, okay, so you've taken a clique, you've deleted a vertex. In that smaller graph, you know it's a clique. You delete a vertex from a clique, you get a clique. But just because you started with a maximal clique in G doesn't mean you have a maximal clique in the projection, okay, in G minus V. It might be that after deleting V, you can take the rest of the clique and supplement it into a bigger clique using vertices of X. Okay, so that's why you need a second case. That's why the inductive hypothesis doesn't do all the work for you. So in the second case, we don't use the inductive hypothesis. We actually use the C-closed hypothesis. This is where we use it. And let me just tell you the key property it gives you. So basically, we want to bound the number of green diamonds that can ever show up. And we can do that because the degree of any vertex in X to N is small. Let me explain why. That's from the C-closed property. I claim that for any vertex in X, it has at most C minus 1 neighbors in N. Why? Well, X is a non-neighbor of V. V and X are not connected. V's neighbors are all of N. Okay? So X can have at most C minus 1 common neighbors with V, because this edge is missing and it's C closed. So that means it has at most degree C minus 1 into N. So that lets you basically project onto these neighborhoods, apply the Moon-Moser theorem, which bounds from above the maximum number of maximal cliques in any graph with N vertices. Here we're using it on subgraphs that have C vertices. And then you add up over all the choices of X. And that's what gives you the rest of the second step. So in the N squared, one of them comes from the fact that in our induction, we only delete one vertex before we induct. So that's one factor of N. The second factor of N is we have to sum over all choices of X when we're bounding the cliques here. So I'll leave you with a slide with some open questions. And so I've offered you a couple definitions of sort of new graph classes, new playgrounds, motivated by this triadic closure property. And if you like these specific definitions, that's great. I think there's tons to do here, especially as some of the questions suggested, more algorithmic applications. I think in general, you're going to need stronger assumptions, extra assumptions, to make a lot of progress here. But I think there's tons of work to do. But even if you don't like the specific definitions that I put forth, that's fine. But I hope you sort of get the higher level point, which is that I think there's a tremendous opportunity for combinatorial type people, like most of the people here in this room, to do some really high impact work in this direction. Right? So I mean, social network analysis, it's really been kind of one of the biggest problems people have thought about in computer science in the 21st century. But for 15 years, the narrative has been driven totally by this sort of competition between these different probabilistic models. There's been almost nothing done on these kind of more robust results, worst case conditions, combinatorial conditions. So I have no doubt that just in this general idea of sort of non-probabilistic models of social networks, there's a ton more to do. So I hope I see some of that from many of you in the years to come. Thanks a lot.
Let's just take a couple of questions. Most of them were asked during your talk.
So this last condition, it sort of feels in some ways a little matroid-like in the following sense. I just wonder, connection. So if I understand right, suppose that you're able to somehow get a clique of size a little bigger than C. Then anybody that connects the C nodes there has to connect to the rest of them too.
Yep.
So you kind of start, at that point you can start to grow greedily, because you can't like make a mistake to add somebody in when you should have had somebody else. Because the other guys are going to connect in, so they have to connect also. So somehow it feels like once you get big enough, you can now go greedy.
Yep.
So it sort of has that feel that at a certain point you can then kind of grab things greedy.
I agree. I mean, if you really wanted the maximum and just not a maximal, it's really not clear to me how you do it without the enumeration. But you're absolutely right. There's sort of this closure property that once you have a seed of C vertices from any clique, you can kind of fill it out very easily. Yep.
Okay.
So it's a bit of an open-ended question.
Yep.
Usually this triadic closure property, we think of it as having some kind of social space, where the vertices are in a metric space, and then if those two guys are connected, then it means that they are closer to each other by the triangle inequality. And I was just wondering whether there is, if there is a connection with what you're doing. This metric space, point of view on one side, and...
Yeah, that's a good question. I mean, if you go back to the original Granovetter paper, his assertion is sort of like a weak qualitative version of the triangle inequality, which says if you have two strong ties, then these have to be connected by a weak tie. So it's like a relaxed triangle inequality of some form. Beyond that, any thoughts, Sesh?
I mean, I think in general, if you have to embed these in a metric space, it has to be a high-dimensional metric space because there are lots of little communities. And so if you try to pack it in a low-dimensional space, then you get too many edges. So
Well, you can always embed in a low-dimensional space. Just what kind of embedding are you looking for? I mean, you can always embed in, I don't know, dimension 3. That's not difficult, but it's just that the embedding is going to be very complicated if you're looking for a smooth embedding or something nice. Also, the way you assign the labels, if it's completely arbitrary, then it's easy, but if you want some kind of...
Yeah, so I'd say the basic answer to the question is we haven't really thought about geometry in this context, and what, is there any interesting geometry in these graphs? I think it might be a fruitful case for making extra assumptions, in the same way that, like, to go beyond the low diameter property, if you want to say a stronger small world property, then you impose extra sort of an ambient metric space, to talk about kind of short and long range connections. You could imagine also here that somehow imposing an extra metric space would be a path to strengthen these conditions to get stronger algorithm results, but we haven't thought about it. So.
Okay, let's thank the speaker and let's take some minutes.